Welcome everyone to Planet Geology. In this video, we will be going through GATE 2022 solutions. In another video, I will also discuss basically what was the examination level, paper analysis, and also sort of like what could be your expected rank. So please keep checking out for that video. And if you have not subscribed to the channel, so please subscribe so that you can get that notification whenever we upload video. So for example, how many marks students are scoring, what sort of like could be the expected rank this year. This year paper was overall a little bit easier than the last few years. 2020 was also a little bit easier. 2021 again was a little bit difficult, especially some questions, although some questions were easy as well. But last year another problem was it was all jumbled up, so a lot of students had problem with finishing up the exam. This year that problem was not there. There was more than sufficient time to finish up the exam, and there was basically proper it came pattern wise. For example, last year there were no MSQs. This year there were MSQs as well. Okay, so anyway, let's go through the solutions very quickly. Which of the following is a typical product of ductile deformation? Okay, so here the keyword is ductile deformation, and the typical product, so you have these options: gouge, breccia, cataclysite, mylonite. If you know basically what happens in case of a fault is, let's say you have a fault here at shallow levels. Okay, so what will happen is at shallow levels you start with a basically narrow fault plane. Okay, and as you go deeper and deeper, that fault plane first of all turns into fault zone, and it keeps on getting wider and wider, and at deeper levels where there is high temperature and pressure, you have ductile deformation. Okay, so at the shallowest levels, here is where you'll get gouge and breccia. Okay, so this is brittle. Okay, then over here you will get cataclysite, and over here where you're getting this ductile deformation, you get mylonite. Okay, this cataclysite is also brittle. Okay, so the correct answer for this question will be mylonite. Now you may ask, why are both these brittle? So the thing is that cataclysite, okay, so this gouge and breccia, they are non-cohesive. Okay, so gouge and breccia, these both of them are non-cohesive, means it will be like powder or broken fragments of rock. Okay, they will not form a cohesive, means it is still intact piece of rock, it is not broken or powdered fragments. So that cataclysite, even though it is brittle deformations, the grain do get crushed, but they are still cohesive, they do not lose cohesion, so this is cohesive. Okay, which of the following coastal erosion landforms is caused by action of sea waves? So you know, ventifact is those faceted pebbles, they will be in wind. Kettle knob and kettle topography, cirque, these are all related to glaciers. So this cliff basically is related to glacial erosion. What happens is, this you will see, for example, a lot of these are there in Western Ghats. So once they asked in the GATE that question on Varkela formation also. So those Varkela are coastal cliffs. So what happens is, let's say you have a highland area and then there is ocean over here, let's say water, and let me draw this, that it is going like this. And what happens is, these waves that you see in here, okay, so they erode this part and these cliffs keep receding backwards. That is another thing that will happen in these regions, so with time. So these cliffs are coastal landforms. This is an easy question, I don't think I even need to discuss that. Which of the following regions of electromagnetic radiation does atmospheric scattering occur? So you know, for Rayleigh scattering, intensity of scattering is inversely proportional to wavelength to the power 4. So lowest wavelength here is of UV, so maximum scattering that you are going to get is going to be for UV radiation. Okay, which of the following is Poisson's ratio for an incompressible fluid? So the key word here is incompressible. Okay, so incompressible means, so what happens first of all, what is Poisson's ratio? Okay, so Poisson's ratio is equal to d, basically transverse strain by axial strain. Okay, so this is transverse strain and this is axial strain, and both are infinitesimally small. So what you have is, let's say you have a block. Okay, now if you compress it this way, okay, what is going to happen is it is going to flatten sort of like this. Okay, so let's say it becomes flatter like this when you compress it. So it has gotten compressed in this manner. Okay, so it has gotten shorter. This is the axial direction, this is axial. Okay, so it has gotten shorter in that axial direction. So I've drawn it like a large amount, but usually it is just for to calculate the ratio, it is infinitesimally small. Okay, so Poisson's ratio, if you know, actually it varies between 0 and 0.5. Okay, so when will it be 0? Okay, so when will it be 0? When, let's say you had that green block, okay, and you compress it. Let me draw it a little bit bigger. Okay, when you compress it in axial direction, the new block that will be formed will be like this. So there is no transverse strain, means no change in the dimension. So breadth does not change. You can see here the breadth is not changing. Okay, so here, has there been any volume change or not? Of course there has been volume change, because area has not increased, but it has gotten decreased from the top. So volume here is reduced. So this is compressible. This one is incompressible. It is shortening in this direction but extending in these two directions. Okay, so it will extend basically to compensate for that shortening, because it is expanding in two directions. So to keep volume constant. Okay, so it is slightly more complicated than that, but it is sort of like to try to give you intuition is that when you're compressing it in this direction, it is expanding in two directions. So that expansion basically goes half in each of those. So here you'll get 0.5 value. And imagine, so this will be 0. So 0 means perfectly compressible. So it is not extending in this strain direction. So it has to be opposite of that. Which of the following periods, so multiple select answer type, belongs to Paleozoic era? So Paleozoic, I think you would already know. This is very, very simple question. It should be Silurian and Carboniferous. It belongs to Mesozoic, and Paleogene belongs to Cenozoic. Okay. The average bulk density of fully saturated, important keyword, sandstone reservoir with a fractional porosity 0.23. So porosity is given to you, which is fractional porosity, okay, is 0.23, and you have to calculate the average bulk density of this rock. Okay, so fluid density is given to you and sandstone density is given to you. So for fully saturated reservoir, the bulk density formula is rho b, okay, equals to porosity into rho f, because fluid is present in the pore space, plus 1 minus phi rho matrix. Okay, so grain density, matrix density is basically density of grains. This is bulk density. So what is going to happen is, if you are going to have a rock like this, so it has, let me draw it in 2D only. So if you have a rock like this, okay, so in between pore space is there, in that fluid may be present, or that pore space could be empty as well. Okay, so the density of this individual grain is rho m, density of that fluid is rho f, and this entire thing, fluid and matrix together, the entire rock sample, it is rho b. So the bulk density will be somewhere in between matrix density and fluid density, and fluid is present in pore space, you multiply it with phi, the rest of the space is occupied by matrix, so you multiply by 1 by 5. So rho b you can calculate, okay, phi is given to you as 0.23, okay, and then you can multiply it with fluid density, which is 1.05 plus 0.77, that is 1 minus 5, into rho m, which is 2.63. Okay, so let me just very quickly calculate this. I have not already calculated it. Okay, 0.23 into 1.05 plus 0.77 into 2.63. Okay, so it will be 2.26. Okay, so the answer that comes out to be is 2.26 gram per cc. Okay, now if they have not given you fully saturated, let's say it is 50% saturated, so it means in this pore space, so rho b, where you are doing phi rho b, so 50% will be fluid, 50% will be air. Air has zero density approximately. Okay, so what you are going to do is, okay, so you are going to multiply with SW, okay, because that is the saturation of water, phi rho f. Okay, it could be oil also. Okay, so let's say the other thing is oil, because air has zero density, so 1 minus SW phi, again rho, let's say this is water, this is oil. So if it is like saturation of water, SW could be 50, it could be 60, 70, 80, and then the 1 minus 5 part will remain same. Okay, so here this part rho phi got divided into these two. This is the part where water is not present, this is the part where water is present. Okay, question number 17. For a productive alluvial aquifer with hydraulic conductivity 105 meter per day and hydraulic gradient 0.1, the flow rate is, so this one is very simple. Okay, so Darcy's law you have studied, Q equals to K dH by dl into area, sometimes also written as KIA, where I is hydraulic gradient. Okay, but here this is the volumetric flow rate in meter cube per day, for example. Okay, or meter cube per second, whatever you want, units you want to keep. Okay, so it will be volume per unit time. But if you divide this Q by A, you get KI. Okay, and this we write a small q KI. So if you divide this meter cube by area, which is meter square, so this you get in meter per day, which is given to you here in the answer. So this is called Darcy velocity or just the flow rate. Okay, so what you have to do is you have to calculate Q. So 105 into meter per day is given to you. Okay, and I is dH by dl. So H is units is height, L is also units is basically length, so they will cancel, so they will have unitless quantity. So that is why hydraulic gradient is 0.01, which is unitless. So the correct answer that you will get in here will be 1.05. Okay, so the next question, okay, although a lot of things are given to you, okay, you have to identify the type of fracture, and it is very simple to identify that because here sigma 3 is vertical. Okay, other things that you are given here is these conjugate fractures. Okay, so these conjugate fractures, I will basically tell you what is going to happen in here. Okay, so what is happening is the easiest way to answer this is just look at sigma 3 here. Sigma 3 is at the center of the stereo net, so therefore sigma 3 is vertical. Okay, so sigma 3 is vertical in this particular case. So you know, if sigma 3 is vertical, then the fault is a reverse fault. Okay, if sigma 1 was vertical, it is normal fault. Okay, and what is the, how do these conjugate fractures develop? So basically if you have a vertical fault, reverse, it could be reverse or thrust also. Okay, so okay, so in this case what happens is, if the faults are like this, okay, so sigma 3 is like this, sigma 1, which is maximum stress, is pushing from here. Okay, and this is fault plane is parallel here, sigma 1. Okay, now a conjugate fracture means there could be another fracture like this here as well. Okay, so you can get basically 2 fractures in total. So this whole part can again come down a little bit like this. Okay, so slipping, so you get these 2 fractures. Now, why is this a reverse fault? So thrust is anywhere not in the option, but thrusts are low angle. Anytime when you have a plane which is low angle, it will appear closer to the perimeter of the stereo net. Okay. Vertical is perfectly in the center, so any steep plane is closer to the center. So this will be a reverse fault where sigma 3 is basically vertical. So this is from Anderson's theory. How many independent elastic parameters are needed to describe a homogeneous isotropic material? This was, I would say, slightly a bouncer question. Okay, so even if you didn't get it correct, that's okay. If you knew it, then very good. But the correct answer here is 2. There are 3 main types of materials based on these like parameters that we have. There is isotropic, orthotropic. Okay, so these ones that you see, orthotropic, and anisotropic. Okay, so these isotropic minerals that you see in here, they have 2 independent parameters. These have 8 independent parameters, and these have 21 independent parameters. Okay, so basically these parameters are what you have already studied. For example, Young's modulus, okay, shear modulus, bulk modulus. So for isotropic materials, they are actually linked to each other by this equation. So out of these, E equals to 3k 1 minus 2 mu. Okay, so what happens is, you see, out of these 3, if you know 2, you can calculate the other one. Okay, the third one. Now in case of anisotropic materials, what you start to have is these moduli you start to have in matrix form. Okay, so it gets slightly more complicated over there. So basically anisotropy is there, so they have different properties in different directions, and if you calculate, do the math, it turns out to be that you'll have 21 independent parameters in case of anisotropic materials. This question I'm not even going to discuss. 21, very simple. Mafic volcanic rock is basalt. The intercept of crystal faces, so intercepts are given to you. Okay, so let's say these are your crystallographic axes. This is A, B, C axis, minus C, minus B, minus A. Okay, so your intercepts on A axis is infinity, so the plane is parallel to A. On B axis it is 2B, okay, and in C axis it is 3C, so it is something like this. So the plane is going, although you don't need to draw this in the exam, but just for visualization, this plane is going like this. Okay, so this is how this plane is oriented. Okay, so you have to find the Miller indices, and the intercepts are given to you. B is 3B, so B will just write 2, actually this is 3 and this is infinity. So intercepts are infinity, 2, 3. Then you have to take reciprocals, which will be 1 by infinity, 1 by 2, 1 by 3, which will be 0, 1 by 2, 1 by 3. And then you have to multiply it. 0, 1 by 2, 1 by 3 has to be multiplied with 6, and you will get 0, 3, 2. Okay, so the correct answer for 21st question will be A. Match the following. So Vajra Karur actually is famous for kimberlites. Okay, and where you get diamond deposits. Anyway, you don't need to know basically all these options. At least something, I think Sukinda you should know. So you have the chromite deposits in Sukinda. Okay, so Q will go with 1. So that eliminates A and B already. Now Malanj Khand, this question came so many times in your test series. You have the largest open cast mine in India. Okay, so in your test series, this question came so many times. So largest open cast mine, and this is basically copper deposit. Okay, so R will go with 4. So basically you cannot eliminate any further. Q will go with 1, R will go with 4. Now this Mangampeta, okay, is in Kadapa. This is also easy actually, because here you get this is one of the largest barite deposits of the world. Okay, so S will go with 3. So the correct answer will be C for this question. Choose the correct statements on seismic wave propagation in an elastic isotropic medium. Okay, P waves are polarized in direction of propagation, which is very true. So they move by basically compressions and rarefactions like this. Okay, so in certain parts they will be compressed, in these parts they get expanded, rarefied, compressed, rarefied. Okay, so the particle motion is parallel to direction of travel. So this statement is correct. S waves are polarized in direction of propagation, which is not true, because S waves, as you know, they move like this. They are shear waves, secondary waves. So they are polarized. So if the wave is moving in that direction, they are polar. They may actually not even be polarized, but anyway, they move. They may not be plane polarized. So they are polarized in direction perpendicular to direction of travel. So this way also they could be polarized. Okay, or any other way like that. Okay, but it is perpendicular to propagation, and if they move through only one plane, then they are called plane polarized. So this is wrong. Okay, Rayleigh waves are elliptically polarized. That is true. So they have retrograde elliptical motion. So sort of like think of this as waves on top of a water. Okay, and this is moving in sort of like the particles are moving like this. Okay, so this is correct. Love waves are elliptically polarized, which is wrong. Love waves, like shear waves, okay, so are actually polarized perpendicular to propagation, but the thing is these are actually horizontally polarized S waves. Okay, so basically if let's say this is the ground surface, okay, so these waves, if the seismic waves are moving in this direction, so the love waves are polarized like this. So they move like snake. Okay, so they are basically perpendicular to direction of propagation and they move. Actually, in reality, we call it horizontally polarized for S waves which occur in earthquake. But if they actually occur at interface between layers. Okay, if that, so here the interface is very strong. You have interface between air and rocks or soil, but many times it can also flow. Let's say if you have two rock layers on top of each other, so these love waves and these will actually can develop between interfaces as well like that. And if the waves are inclined, then they may not be horizontally polarized. They will be polarized parallel to that discontinuous plane in between. The difference in arrivals of P waves and S waves generated by earthquake are recorded at time station as 1 second. So delta T is 1 second. So basically in an earthquake, the first waves to arrive are P waves and then S waves arrive. Okay, so this is P and then S waves will arrive. Okay, assuming homogeneous isotropic earth, Vp is given to you as 3 km per second. Vp by Vs equals to 2, which implies Vs equals to Vp by 2 is 1.5 km per second. So the distance between station and hypocenter is, so earthquake occurred at the focus inside the earth. Okay, so from here to the recording station over here, so these waves traveled. Okay, so P waves arrived first. After that S waves arrived. Okay, so they're lagging behind. Okay, so you're given this. So this is very easy question. Assume that the distance to hypocenter is x. So let's say this is the station and this is the hypocenter or focus, is basically the same thing. So the distance is x. Okay, so let's say time taken by P waves will be x by Vp, which is 3. Okay, time taken by S waves will be x by 1.5. Okay, so delta T will be Ts minus Tp, because S waves will take more time. Okay, is equal to 1 second. So x by 3 minus x, sorry, by 1.5 minus x by 3 equals to 1. Okay, so which implies you can actually solve this for x, and the answer that you're going to get is x will be equal to 3 kilometers. Okay, so basically here you can take 3 as LCM, so it becomes 2x minus x equals to 1, so x equals to 3. Assuming rate of rotation of Earth is given to you in radians per second, so it is the angular velocity which is given to you, not the linear velocity, and the radius of Earth is given to you as 6371 kilometer. The centrifugal acceleration at 60-degree latitude for a spherically rotating Earth you have to calculate. So this question, even if you have not studied, you can actually solve it if you know the formula for centrifugal acceleration. So what happens is, here at equator, okay, and let's say you go at poles. Now Earth takes 24 hours to complete this rotation. Okay, so angular velocity is basically angle in radians divided by time. Okay, so let's say it is 360 degrees, which is actually 2 pi radians, divided by 24 hours. Okay, so that should be the rotation velocity of Earth. You can calculate, it should come out to be somewhat closer to this one. Now this is angle because whether you are here at this point or at this point, you are covering 360-degree angle or 2 pi angle. But what is the difference? Okay, so what is the main difference? The main difference is, here you see the distance that needs to be covered is so large, whereas the distance at this point is very small. So now they have not given you that, they have given you, asked you at 60-degree latitude. So that is important, 60-degree latitude. Where will you find 60-degree latitude? Okay, so this is 0-degree latitude, poles are 90-degree latitude, so 60-degree latitude will be somewhere here. Now at this point you can see that the circle that is formed here, okay, will have a shorter radius. This will be the radius. Okay, let me use same red color for it. Okay, so this is the radius of the Earth at equator. So RE is given to you 6371 kilometers. Okay, and the one that you see in here is again RE. Okay, so it is the same radius everywhere because we are assuming spherical Earth. Okay, now this is, let's say, R at 60-degree, at we can call it R lambda. Okay, radius parallel to equator. Okay, but at 60-degree. Last year a question came. Okay, there they did not ask this R, they asked this R only. Now you may ask, like, why was this different in that question and here we are taking to be equal? Because here they are asking you to assume the Earth to be spherical, but actual shape of Earth is not spherical. So if this is just an assumption. In reality, the radius will decrease when you go to the poles. Okay, but here we will assume it to be equal. So R lambda you can calculate. What will R lambda be? So you know R lambda, so if this angle is 60-degree, this angle will also be 60-degree. So R lambda will be equal to, so R lambda by RE will be equal to cos 60-degree. So R lambda will be equal to cos 60-degree, which is 1 by 2 RE. So RE by 2. That is the value that you are going to get in this answer. Okay, so, and you know, centrifugal acceleration alpha is equal to omega square r. Okay, acceleration, centripetal acceleration, so this is angular acceleration. Okay, sorry, centripetal acceleration. Centripetal or centrifugal, both will be same. Okay, or acceleration, you would have studied this. Okay, v square by r. Okay, so this v square by r is the acceleration, and if the velocity is known to you, if angular velocity is known to you, then it becomes omega square r, because you know v equals to omega r and omega square r square, and then r will get cancelled here. Okay, so this is the basically formula that you have to use. And acceleration alpha, if you have to calculate, omega is given to you, so it will be 27.27 into 10 to power minus 5. Okay, so you just square this term, okay, into m, you just have to multiply it with r. R is basically RE by 2, which is 6371 by 2. Now remember, this is in kilometers, everything is in meter per second, so in SI units, so you multiply with 1000 also. Okay, so the answer that you are going to get if you do this calculation, okay, so you can calculate it with the exact answer will be in this case. So it will be 7.27. So 7.27 squared into 10 to power minus 10 into 6371 by 2 into 1000. Okay, so it will really be 7.27 into 7.27 into 6371 by 2 into 10 to power minus 7. Okay, so they've asked you in 10 to power minus 3. Okay, so you basically are going to convert it into that. So you can divide it by 10 to power minus 3. So this will become 10 to power minus 4. So then you just calculate it. Okay, so let me just calculate it. So 7.27 squared, okay, into 6371 divided by 2. Okay, so it will be 168362. Okay, so 8362 into 10 to power minus 4. So you can write it as 1, 2, 3, 4. So it will be 16.83 into 10 to power minus 3 meter per second square. So I'll keep it into 10 to power minus 3 as well over here. Okay, so this is what we are going to get for this question as answer. Now the angle of inclination of remnant magnetization of a volcanic rock measured at a location is 45 degree. Okay, so the paleomagnetic magnetic latitude of the location, this is a repeat question from previous year. Basically what happens in this question is, so if this is Earth, okay, so you know that the gravitational field around Earth goes something like this. Okay, so what is latitude really? Okay, so now you see here, okay, so at equator, okay, so latitude is 0. So you can think of latitude as being basically the angle, sort of like here this 0 degree is sort of like this line joining north south. Okay, here this tangent will be like this, so this angle will become 90 degrees. Here the angle with this north south line is 0 degree. Okay, now the same thing you can do is you can calculate that using this magnetic field as well here. Okay, so this will give you basically this angle that you'll get here. Okay, so you can imagine that line. Okay, and here it will be like this. So this is magnetic inclination, right? Okay, so and then the one that you're going to get here will be latitude. This is will call lambda. Okay, so the relationship between them is given by, okay, so the formula is very simple. Okay, it is tan I is equal to 2 tan lambda. Okay, so what you have to do is you have to calculate the angle of inclination of remnant magnetization is given to you, magnetic latitude of the location of volcanic rock. Okay, so you have to calculate the latitude, inclination is given to you, angle of inclination. Okay, so tan I means tan 45 degrees equals to 2 tan lambda. You have to calculate, and tan 45 degrees 1 by 2. So lambda will actually be tan inverse of 1 by 2, which is 0.5. Okay, so the answer here will be 26 point around 2 degrees. Okay, so I'm not going to calculate it, you can calculate it yourself. Coarse grained igneous rock contains 25% olivine. I think you all know the classification scheme for ultramafic rocks. Okay, so you have olivine, okay, CPX, OPX. Okay, so you have 55% olivine. Okay, so this line that you see in here, okay, so this line is at 40% olivine, or you can think of it as 60% CPX, and on this side 60% CPX on this side, actually that should be OPX. Okay, so 55% olivine will be zinc. So olivine, it's actually at, yes, that is correct. Okay, 40. Yeah, that 40% olivine was correct. So 55% olivine will be northward of that. Okay, and 25% augite. Okay, so and 20% enstatite. So right in middle. Okay, so somewhere here that point will plot. Okay, and this is actually learzolite. Okay, learzolite is a type of peridotite. Okay, the rock type used for building Red Fort is fact-based question, sandstone. Okay, so this you can see is learzolite basically. All these virelite, Harzbergite, Dionite, these are all peridotites. These which rocks, ultramafic rocks which have less olivine but more pyroxene are called pyroxenites, and these are different types of pyroxenites. A rock rich in just pyroxenes, orthopyroxene, clinopyroxene is called websterite. Question number 29. During crystallization of magma, which of the following schematic paths between 2, 3 and 4 describes the behavior of compatible elements in the residual melt? So basically what is happening in this is, let's say you have a magma chamber. Okay, from that magma chamber, so let's say this is the magma chamber. So it will have certain compatible, incompatible elements, let's say. Okay, actually there is no need to even draw this big. Okay, so what is now going to happen is, during crystallization, which of the following paths represent behaviors of compatible elements in the residual melt? This question first of all is just like choosing odd one out. You know, the only odd thing here is 4. Okay, 2 and 1 are on the upper side. 3 is when you have degree of fractionation. Okay, sorry, when you have distribution coefficient equal to 1. Okay, so basically what is happening is, from this magma some minerals are forming. Okay, so this is the solid part which has formed. So you are asked compatible elements. So what will happen to the compatible elements? Let's say this compatible elements, they will go into the solid phase because they are compatible. That is the definition of compatible ones. Okay, now what will happen is, okay, so this residual melt, and you remember that in case of plagioclase crystallization as well, okay, from magma, what happens is this Na is relatively more incompatible than Ca. So you can see here in the rock, the concentration sort of like of the incompatible one in the residual melt keeps on increasing, whereas that of the Ca, it keeps on decreasing. So basically what is going to happen is, so when you start here, okay, so they are asking you in the residual melt, what is left behind here. Okay, so the more and more crystals you will form, the compatible elements will keep on getting enriched more and more in the solid phase. So they will keep on getting depleted in the melt. So if they keep on getting depleted in the melt, so the only curve that shows you is 4. So the correct answer will be B here. In geological map of India, which of the following units has largest area? I think this is easy question. Deccan Volcanic Province. So if you know that sort of like map of India, okay, so this whole portion from here to even Gujarat, okay, and even underwater also, so this large portion, Andhra Pradesh, Madhya Pradesh, even some part of Rajasthan, this is all Deccan Volcanic Province. Okay, and others, for example, Singhbum granite. Okay, it's not even asking Singhbum craton, it is just asking Singhbum granite, which is intrusion in Singhbum craton. So it is actually pretty small compared to Deccan Volcanic Province. Mesozoic rocks of Kutch. So Kutch is just this much area, so small. Vindhyan supergroup will be here. It is also much smaller than either of these. Okay, so it's actually not as extensive as compared to Deccan Volcanic Province. Okay, so let me just show you an image as well. Okay, so this was actually from my own paper from Mumbai High, but okay, this does not cover the entire area, but shows you sort of like what what is the extent of some of these rocks of these Deccan traps. Okay, I think there is some issue with this copy paste option. Anyway, let's just keep moving. Okay. Which of the following cross stratification provides the paleocurrent direction of truncated bedding of an undeformed cross stratified sedimentary strata? Okay, so this is a question which has something, basically a little bit of material to pack, one of the like challenging questions until now. Okay, so cross stratification provides paleocurrent direction on the truncated bedding surface of an undeformed cross strata. Okay, so basically let's assume, okay, so in 3 dimensions, how will these cross strata look like? So tabular cross strata, okay, will really look like, so they will have top and bottom surface will basically be straight line. Okay, so if they are like just what you're going to get is these cross strata. Okay, so they will be like this, cross stratified layer. Okay, so here they will appear just like this. So you cannot really tell, okay, in this truncated strata which way will be the current direction. Okay, how many cross stratification, herringbone, they have actually bidirectional. Okay, and even they will be something like this. So hummocky cross stratification, sorry, this herringbone cross stratification will be like this only. It can be tabular also, and then it will actually give you 2 possible directions of current. Okay, paleocurrent. But in the truncated, okay, undeformed means it cannot be soft sediment deformation. Okay, and truncated bedding surface, for example, from here, if you're looking at it, can you find the paleocurrent direction if you look from here? So here basically what happens in case of trough cross stratification? So trough cross stratification in the truncated strata, they will look something like this. Okay, so basically the top and bottom surfaces are like this. Okay, and the cross strata will be like this. Okay, so the bounding surfaces of the cross strata are curved, and you can use that curvature to find out the paleocurrent direction. Which of the following is a dinosaur? Is an easy question. There is a saur here. So here also there is only one option with saur. So you choose this one. This one is actually an ancestor of, whenever you see this megalodon, mastodon. So these are all basically proboscidae. Okay, basically from when you study it in evolution of elephant. Mammoth, this is horse, this is cephalopod. Okay, Hooke-Brown criterion. Okay, so your basically Mohr-Coulomb criterion is a straight line. So Hooke-Brown criterion is not a straight line. So this is the failure envelope. Okay, first of all, failure envelope cannot be an ellipse. It will not be a straight line because this is the Coulomb criterion. Okay, so the Coulomb criterion, so if you remember, it looks something like this. Okay, so this is the Coulomb criterion. Here you have Mohr circle. Okay, how will a elliptical failure criterion? You have never seen this kind of a failure criterion. In reality, the failure criterion actually behaves more like this. Okay, so this can be defined by, let's say, Hooke-Brown. Okay, so as you see, these two options go away. It has actually a parabolic shape. Hyperbolic shape, usually it will get parallel to, if it was getting parallel to this line somehow, then it would have been a hyperbolic shape. Okay, so how do hyperbolas look like? For example, you have seen one of the easiest examples of hyperbola is 1 by x. So y equals to 1 by x looks something like this. Okay, so they usually get parallel to these perpendicular lines. This is called asymptotic. Okay, All right. So we will finish the first part over here. Okay. And in the next part, so first 33 questions are done. So actually, sorry, first 23 questions are done. In the next part, we will cover in the second part of the solutions in the video. Okay.